Hello to everyone. Welcome to the GMI Intrinsic Safety 6 Common Mistake Seminar, webinar. Good afternoon to you, good morning or good evening, wherever you guys are. We have a very full schedule today. We had booked out from people from all over the world. I hope you're doing okay. You know, me and Bob are doing okay. We're going through this COVID and we are okay. So I see that most of you should be in. We have a lot of you guys here. So Bob, let's start our presentation. We are going to, let me first introduce Bob. Bob has been in this world for many, many years. You can see his gray hairs, but we have a similar age. After his graduation over 30 years ago, he went on to several positions and now he's president owner of IEX, Source IEX. And
that's correct.
Right, and he's also an instructor for the CompEX and the ICEX CompPC scheme. He's done several jobs as an inspector, third-party inspector around the offshore and onshore in the EX domain. And he's also a member of the ULSTP for the adaptation of the 60079 standard. So he is very, very, very qualified to run and to be our speaker today. Okay, Bob, before we go on to our webinar, let me give you a few words about GMI, who we are and what we do. We are a safety company. We design, engineer, and manufacture a complete range of intrinsically safe and seal certified devices for different automation packages, DCS, ESD, fire and gas, PSC, and so on, in all the industry, from oil and gas to food and beverage. We have over 40 years of experience, and we are manufacturing 100% of our product here in Italy. So we're very proud of that. Oh, by the way, I'm sitting in Italy, and Bob is sitting in Houston, Texas.
Spring, Texas.
Spring, Texas. Okay, let's be accurate. We are, however, a global player with presence in 5 different continents. Let's go next. What we do is we take care of safety. So for us, safety is a responsibility. That is why we put a lot of effort to try to have a high quality product. So our product, we use the state-of-the-art technology to have full traceability. We do full 100% testing on every single item that comes out of our factory. We are, of course, ROS, REACH, and whatever else compliant. And our factory and our product and our company is SEAL 3 certified with the SC, Systematic Capability 3 certification by TUV. You can read about our responsibility, social responsibility, but basically what we're trying to say is customer satisfaction should come while strive to make the world better. Next, Bob. Okay, sorry. These are the products we manufacture. We have IS barrier, safety relays, isolators, power supply. Also, those are SEAL 3, SEAL 2 certified. We have multiplexers. We have custom termination board, hard interfaces, surge protector, SPDs, some loop indicator. And last but not last, we also have a division that provides training and services in the functional safety and now soon in the EX domain as well. Let's go next. This is us. We have 8 subsidiaries around the world, from Dubai, Russia to China and anywhere else. We have many distributors. We are about 200 people. We do many, many seminars. Now, of course, we stopped that and we're doing more webinars. And we have thousands of installations around the world, and the list of our customers, it's coming up next, which is basically we interface all the system vendors around the market, from ABB to Yokogawa, And we have worked with many, many EPCs. We do a lot of also seminars and education for them. We work with OEMs all over the world. In Texas, we have many from Canary, Halliburton, NOV, and we work with many end users, possibly with some of you guys already. Next.
Oh, sorry.
Great, Bob got carried out away. Okay, so that's it. So now it's my time to turn this over to Bob and let him do this presentation. Before I do that, let me give you a technical indication. We have taken your questions that you have submitted during the registration phase. After the presentation, we will answer those. At the same time, you can post questions at any time during this through the question and answer box. You have a button there, question and answer. You can go there, type your question. You can leave your name or you can take it out. It doesn't matter to us. And we will try to answer them through the presentation or after the presentation, either live or type, depending on the question. We might have already answered most of your questions, so they might be already prepared and answered, so I might not answer right away. But anyhow, you're welcome to pose any question. We want to have this an interactive webinar. Of course, we cannot let you talk because there's too many of you and then nobody will understand anything. Okay, Bob, you can take it over.
All right. Thank you, Paolo.
Welcome.
And again, as Paolo mentioned, good morning, good afternoon, good evening. Here in Houston or in Spring, Texas, it's 9:07. We should spend probably about 25 minutes going through the presentation. So we should have some of the questions that have already been asked that we'll start spending some time going over all that good stuff. Without going into too much details on the fundamentals of intrinsic safety, and if you did not participate in a previous presentation that was done by Paolo and Andrea, please go to YouTube or go to the GMI website and you can rewatch or watch the presentation on intrinsic safety. When Paolo and I discussed a little bit about what a topic I thought might be of interest, I thought possibly some of the things that I see as an inspector or as an instructor of some of what I would consider be some of the little faults that come up, because many of you, I understand, are probably designers or implementing IS into your systems. But when it gets out into the field, sometimes we have problems. So this is really what I wanted to focus on, is some of the issues with regards to intrinsic safety. Even though we bring it all together and we make it all perfect in a nice, clean environment, once it gets out into the field, sometimes it doesn't hold true. So a little bit about the standards, rules, regulations. There are, multiple different standards, rules, regulations worldwide. The one that most of you are probably familiar with are the IEC standards. And however, in the United States, we follow the NFPA. It's commonly referred to as the National Electric Code. In Canada, they follow the Canadian standards. In Europe, we follow the EN versions. And of course, worldwide, we have different variations of them. So this slide just kind of summarizes a little bit about what are the relevant standards that we follow for either the design or installation of IS. Again, in the US, we follow what is called NFPA 70. That's commonly referred to as the National Electric Code. Article 504 gives us all the details as far as what are the requirements for installation and design. We have a new UL standard that's actually been developed, and I was part of that committee, on inspections of EX equipment, which includes information on inspections of intrinsically safe systems. In Canada, it's the C22.2. On the international side, we have a bunch of different IEC standards that we really have to comply with. The main ones for IS really fall within the -14 standard, which is our design of EX installations, as well as 25, which is design of IS systems. So there is a little bit of a difference. There is some overlap. There's a significant amount of overlap between the two. But basically, if we follow the requirements of the -14 and the -25, that's really going to be the main stuff. 17 is our inspections, which again include IS. And of course, in Europe, we follow the EN versions, which basically are pretty much identical to the IEC standards, with the exception of information that is written in annexes. Now, you may find in various parts of the world, including the United States, that will also reference IS in other documents. So if we're doing something in the offshore market here in the Gulf of Mexico, we may follow some API, American Petroleum Institute recommended practices. There's also a set of IEC documents, the 61892 standards, that are specifically around mobile and fixed offshore units. So the point is, and really there are a lot of standards and there are a lot of regulations that are involved. The good thing is that majority of your installations when it comes to intrinsic safety are very, very similar. So the rules and regulations of what you would find, say, in the United States versus Europe versus other parts of the world, there's going to be a lot of commonality. So that comes to our first poll question. So,
wow,
what is
we have some questions. So we have to, sorry Bob, I interrupted you. Let's see if you guys understood what he said. Well, let me launch a poll so they can answer these questions. What is the question, Bob?
So
launch a poll.
What is the international installation standard recognized for the installation and design of IS systems?
All right. So guys, let's see if you know this. I can see, wow, the polls are coming in. It's, honestly, I don't have the answer, Bob. I don't know the answer to this one.
Well, we'll give another couple seconds just to see if you guys were paying attention.
Yeah, it's still coming in. We still don't have 100%. I think it's still moving. We have about only 40% of you guys voted. Let's see if you get a little more answer. I'm a sales guy, so you know I'm not supposed to know all of this stuff. It's your. I don't know if did you see somebody come live earlier into our webinar? A little picture showed up.
I did
something
not.
Funky happened just a moment ago. I don't know what happened. All right.
It's Zoom.
We cannot keep all day here, so let me close this poll and see what it looks like. Share result. Here we go. Do you guys see the result? Bob, do you see the result?
I see the results. So just to emphasize here, again, the correct answers in this case would be the -14 and the -25 standards. So there's actually two correct answers. 17 is really, again, that's our inspection standard. You could argue that the NFPA and the CSA documents, standards, rules, regulations are actually also correct. Although I did reference it from an international standpoint, so I don't think of the NFPA or the CSA as really being international. These are more homegrown, but obviously our audience is around the world, so you could say quite rightly that the NFPA is an international standard. So really, honestly, the first two and the last two are all correct answers. 17.
So most of you guys answer correctly anyhow.
That's correct. That's correct. So
all right, so we can move forward. Share result, no problem. Okay. Okay.
So again, this is that slide again, just to reference, and I won't go through this again. Now, one of the things about intrinsic safety that is important, and as we teach COMPEX or we teach under the IEC EX COPC scheme, when we look at all the various protection concepts that are out there, such as EXD or EXE or EXP, they're typically standalone products, if you will. One thing that we always emphasize on intrinsic safety, it is truly a system concept. As a system concept, we must take into account all of the various components that are part of that system. So we typically take our control circuit, our cable, our junction box, our field device. Our barriers are really considered to be what we would call associated apparatus. So if somebody uses the term associated apparatus, that's typically another reference to an intrinsically safe barrier. Sometimes we could have a junction box, a marshalling box of some sort that's located either in a safe area or a hazardous area, and then obviously the field device. But we also have to take into account the cable, and certainly we have to take out whatever parameters that we have from the control circuit. So that's our system concept. There are basically two main types of associated apparatus. On the left-hand side, you'll see what is called a galvanically isolated type product. On the right-hand side, you'll find a Zener barrier type. Again, there was a webinar, a really good webinar that Paulo did here not too long ago on somewhat of the differences, the similarities. The original IS products that were developed after some of the early mining disasters that took place in the UK were around the original Zener diode type concept. The galvanically type products are a fairly new development, and I say fairly new. They've been around at least for 20, 25, maybe 30 years now. So they're two different products. They do basically the same thing. They're both considered associated apparatus. An easy way of telling just by looking at a particular product, what you'll actually see down on the right-hand side, and I don't know if you can see my mouse, but you'll see these little tabs here.
Yeah, we can see the mouse, Bob.
Okay, thank you. So that's basically somewhat usually a dead giveaway that's telling you that most likely that's a Zener barrier type. And that's used, if you will, for providing your IS ground. So the galvanic isolator concept, basically the main difference is that we have in effect a transformer, in effect a safety transformer that's located between the potential source and the device in the field. We still have things like current limiting resistors, we still have Zener diodes, but basically we're replicating that signal, if you will, from the safe area into the hazardous area. When we look at a galvanic isolator, what happens under a fault condition, if we have a fault condition, it stays generally, it's going to be in the non-hazardous location or in the area of lesser hazard because it's protected by the use of a safety transformer. You'll see on the very lower left-hand side, isolation is not required for that IS circuit. Now, when we look at a Zener barrier basically has three major components. We have our protecting fuse, we have our current limiting resistor, and then we have our voltage limiting Zener diodes. So diodes, basically, the concept is that think of them as like a lock in a dam. When we have water getting too high in a dam, we need to release that water. We open up our gates to allow that water to rush out. The Zener diodes do basically the same thing. Once the voltage achieves a certain level above the threshold, then those Zener diodes open up. They allow any of that excess voltage to pass through ground. Notice on the right-hand side that we must have with Zener diodes a good ground connection, typically 1 ohm or less maximum of our resistance. So that's typically how our Zener diodes will act. Now, obviously, during a situation where we have a high inrush current, we have our, excuse me, our current limiting resistors, and we also have a fuse. Now, here's the issue under a fault condition with Zener barriers. If, in effect, we do not have a good earth, right, or a disconnected earth, we potentially could be taking an earth fault onto the dirty side, or we don't have good isolation. And so, therefore, it is very, very critical that when we use Zener barriers, that we must have a dedicated IS earth. And as we'll talk about some of the mistakes that we see in the field, this is in many cases one of the biggest issues that we run into when we do inspections, is the quality of the earth or whether or not a dedicated earth is actually there.
Sometimes it's actually completely missing.
Simple little poll question.
Oh, okay, here's a new poll. Okay, let me launch this poll. So what device can typically be installed in conjunction with an IS barrier? Well, that is, for me, an easy one, since I've been selling many. So the poll is on, guys. Try to answer this question. It's a multiple choice, so you can select the type that are correct and some are not correct. I might give it away. High power does not fit with barriers. Huh?
Right.
They're inherently low power. Well, it looks like you guys are answering correct. I don't see any wrong answer. Well, I do see some, a little small answer. Okay, should I, we got, oh, it's still coming.
No, we're still getting answers.
Yes, you get an answer. Let's let it run. I hope you guys are enjoying so far. There was, Bob, a question that I did not pull up earlier that I should have. While the poll goes on, it said one note, please note the standard CSA C222, number 157, is not for installation in Canada. The co-practic in Canada is CC. Okay.
Okay.
Sound correct?
Well, we'll take a look at that.
Okay, we'll take a look at that later. Then we have other guys type on that question, but without any question. So I dismiss that. All right, let's go and see what else is there. Let's complete our poll. And the poll, share the result. Well, 65% of you answer transmitter. That is 100% correct. Simple device was also very correct answer. Not too many of you picked that out. And what was B&D? B&D was the right answer, right?
That's correct. Yeah. So
yeah, B&D was the right answer. Yes.
The most correct answer, right?
The most correct answer.
So an EX light fitting, generally speaking, we're talking about what power we're talking about that will actually be allowed through based upon the ignition curves on intrinsic safety is about 1 watt of power. So we're way below the power that we would need to either operate a motor or an EX light fitting. But certainly things like a transmitter, a simple device, absolutely we can use intrinsic safety. It's not the only method, but certainly those are prime examples of types of devices that will make intrinsically safe. There was actually an interesting point, and yeah, we can share or stop sharing the results.
Yeah. Well, I had a question. I mean, some of you guys said none of the above. I mean, what the hell? What can a barrier be used for? Now I got a beep in my webinar that we gotta take it off. Stop share result. Okay, let's move forward.
All right. So getting into the common mistakes, and I've already given you this hint, right? No dedicated IS earth. Zener barriers, in order to work properly and safely, do require a dedicated earth. So again, a clean earth is attached to dirty earth, and in some cases, a Zener barrier has no dedicated earth. And again, that resistance for clean earth needs to be no more than 1 ohm resistance. So when we look at an installation, and this picture here is showing a attachment, in effect, of a Zener barrier onto a piece of DIN rail. Well, the DIN rail can also be used as a means for earth. And I've seen some installations where the DIN rail is actually then attached to the enclosure. And if it's a metallic enclosure, then that is typically tied into our dirty earth. So we want to make sure that when we are utilizing Zener diode type barriers, and if we're mounting them to a DIN rail of some sort, we need to make sure that that DIN rail is isolated from an enclosure. Assuming we're using a metallic enclosure, we have to have proper insulation. So this is one of the biggest issues that I do see when I go out and do inspections on intrinsic safety with regards to Zener barriers, is not having a dedicated IS earth. So on our right-hand side, we'll see intrinsically safe going out this way. We have our safe area wiring coming out this way. We notice that we have dedicated earthing, and we have our IS earth, and then that's separate from our normal dirty earth. So that's typically one of the biggest issues that we do find. And quite frankly, this is also a reason why a lot of people don't like using Zener diode barriers, is because of the fact that generally speaking, when we use them, then we have to ensure that we do have a good clean earth. The second one is the segregation between intrinsically safe and non-intrinsically safe circuits. So in this enclosure, what you're seeing is that we have our glands, or at least we have our cabling marked. We certainly have some loops going in. And in this case, we have an enclosure strictly with intrinsically safe terminals. So everything looks fine. There's no conductive parts of the wiring that are shown. One of the things that is always good engineering practice, and one of the things that we do look at when students come through and do training, is that we do not want to see more than 1 millimeter of copper showing out of a bootlace ferrule that's going into a terminal block. Okay, so we want to keep any exposed metal from our bootlace ferrules when we're terminating those into terminal blocks, regardless if it's IS or non-IS, we want to keep that to a minimum. So looking at this installation right here, this looks great. Here's another example where we have our field wiring coming in from the top, going into the top of, in this case, galvanically isolated barriers. And then down on the blue side, if you will, that's our exit. And that's going out to the field. So again, everything looks fine, everything looks good. But when we start seeing this, now here we have a situation where somebody has taken the wiring and now doing service loops. And it's very easy to do this, and it's very easy to understand in the field, because we want to make sure that if we've done something wrong, we have plenty of excess conductors to make our connections. But now what we've done, we've violated in effect that distance requirement between IS and non-IS. So if we see here, we basically have screwed up, even though the design was fine, but during our installation procedure, we didn't have a good segregation between IS and non-IS circuits. This is a simple example. This is a panel with a single barrier. And again, if we look down at the bottom, we see our IS coming out, we see some power coming in. But then all of a sudden, we've taken this IS circuit and we've looped it up into some sort of duct, and we've run that right next to probably some power conductors. So we need to have a separation between power and IS. And there's different ways of achieving that we'll talk about.
Definitely not good there.
Thank you, Paulo. There you go. So here's an example on the left-hand side where basically we have our power and our IS separated, right? We have different duct, and we have our IS terminals on the top, and we have our power terminals on the bottom, and we've maintained a separation. Now this on the right-hand side, you can see we have some intrinsically safe barriers here, and we have a power unit of some sort. I think in this case, this was a contactor. We do have a partition, right? We have a partition located right here. So when it came out of the factory, they put a partition to maintain a separation between IS and non-IS, which is certainly allowed. However, during the installation, what we find is that we've taken some of these cables, we've looped them around, and in effect, at this point right here and in other points, we've now violated that 50 mil separation. Now, in this particular installation that I saw, these were all packed with barrier glands. So as you might imagine, the repair to try to fix this was not a simple little thing to do. So, you know, we want to make sure that the technicians that are doing our installations are making sure that they're following that 50 mil separation between IS and non-IS, okay? This is a big issue. Here's another example where we have, in this case, we have a combination of both IS on the right-hand side and non-IS on the left-hand side. Again, we have a little partition right here, which is good. We have our earthing terminals, fantastic. But the moment we start doing all of this good stuff and we start interfacing our IS with our non-IS, we've now defeated the purpose. The reasoning behind the separation and segregation between IS and non-IS circuits is to make sure that we have no inductive currents that could pass from a power conductor into an IS circuit through air, right? So we have to make sure that we segregate our IS and non-IS, because we do not want that to take place. And there are different ways.
In addition, Bob, if any of this wiring which has current that is uncontrolled because it's non-IS, they could melt down and melt the cables, you know, the IS cable, and make a short circuit or whatever, you know.
Absolutely, absolutely.
It's mandatory, it's an absolute requirement. And as GMI, we are designer of products. It's a limitation we have. When we design, we always have to keep 50 millimeter between anything, you know, even in the design of the circuit itself.
That's right. And people ask sometimes why barriers are designed, or at least the distance between the incoming and outgoing. And I think we may be able to show it here, at least partially. This distance here between the outgoing and the incoming has to meet a minimum requirement. So all barriers will have at least that distance. And as you might imagine, I think we have a polling question. what is the distance requirement for IS and non-IS circuits within the same
Let me
enclosure
launch this
segregation?
poll up. Let me see if I can find it. All right. Here we go. So the question is, what is the distance? Well, now the answer must be, if some of you don't get the right answer, I get mad. Yeah, we have, well, then I cannot get mad. So the answer is Enclosure from a segregation standpoint. Okay, let's end the poll. I think most of you have voted. Still a few coming, but okay, let's end poll now. Share the result. I would say 90. What does it say there?
So we have 25, 40, 50, and 80, and a vast majority of you did recall that it is 50 millimeters. So
50 millimeters is a number, as an IS guy, 50 millimeters to stuck to your mind.
Well, or 2 inches, you know, we like to say in the United States, right? So 50 millimeters is that number. So we want to make sure that we remember that number when we're talking about the separation between IS and non-IS circuits. Now, I mentioned to you there are different ways to achieve that 50 mil separation. And I'm going to close the poll.
Yeah, close the poll. You can move forward.
Right.
Okay.
So here's a good example that we show in this case, this panel. Again, we have a separation between IS and non-IS circuits. So that 50 mil could actually be up and over a segregation partition of something like this. It could be a free air. Or when we're talking about actually cabling and going and using those cables, we can actually use shielded cables, especially when we're talking about cable runs into trays and things like that, or armored cables. One of the things that we cannot do is that we cannot run IS and non-IS circuits within the same cable. We can run IS cables next to control cables, but we have to maintain either a 50 mil separation where we're running them in cable trays or cable ladders, or we have to make sure that one or both typically are armored or shielded or both. Now, everywhere in the country is slightly, or everywhere in the world is slightly different with the requirements, but generally speaking, we all agree on a 50 mil separation. So realize it can be done in many different ways.
Bob, I have a question. Myself, I have a question. I see some questions have come up, and I will try to answer those. But is it not true that if the partition is metal between the IS and non-IS, has to be grounded?
Yes, typically it would have to be grounded. Yeah, you'll see.
In fact, somebody's asking if we can reduce this distance without applicable for wire duct. I'm not sure about your guys' question. The distance of 50 millimeter can be reduced if question only at the end of the presentation, lol. No, you can make question, guys, but you have to complete the question because if it has no answer. But anyhow, you within the same cable duct, you need to keep a separate 50 millimeter. But if you run two different cable ducts, do they have to be? Can they be next to each other? Also 50 millimeter apart.
Well, the segregation you're saying as far as the duct is concerned, Paulo?
The cable duct, cable tray. Sorry.
Right. Well, generally speaking, we would have those ducts at least 50 millimeters apart, so we can visually tell that we've maintained that 50 millimeter separation. There's nothing in the standards for the most part that say that we cannot run IS and non-IS in the same duct, but it would have to be a very wide duct, and we would have to bundle the IS on one side and the non-IS on another side and make sure that we're keeping, again, that separation. Okay. There was a question. I believe somebody asked about a 6 millimeter separation.
Yes, somebody asked about a 6 millimeter.
Yeah, there are some requirements with regards to IS. There is a IS to IS separation, and actually 6 millimeters is the separation requirement from IS circuits, from one IS circuit to another. So when we actually go back and look at say, for example, a junction box here, what we see, terminal blocks actually meet that 6 millimeter separation between one terminal and another terminal. Now, there is also a requirement that the IS circuit itself must also be separated by 3 millimeters from a ground source, if you will. So we could take these terminals, we could put it literally right up next to this enclosure, and we meet that 3 millimeter separation, okay? Now, generally speaking, I wouldn't say do it just because you want to leave yourself some space, but doing all that stuff. But basically, EX terminal blocks are built with that 6 millimeter separation, as well as the 3 millimeter separation between the terminal and earth.
Okay.
So,
there was some question about power cable and IS cable. Obviously, they cannot be cross each other. They need to be kept separate, as we just discussed. So we get that answer live.
Yes, to an extent, although we can have power cables with armor that can be used as a means of separation, segregation. What I would say, however, in any of those situations, again, the standards are basically written very similar, but there may be clients around the world that will say, I do not allow that. So realize what we're telling you here are some of the generalities, the commonalities with a lot of standards, but always, always, always make sure you find out what is the relevant standard, what is the requirement for your country, what are the specific client requirements, or what are your requirements that you put in to make sure that you're in compliance. Because
and
again,
Bob answered the question that just came up, so we're doing good. Which you said, industry practice is to separate, but what about there are any other references? Well, every country has its own references, and you have to follow those, right?
That's correct.
Okay.
All right, let's move on. We'll answer some more questions as we get further on.
Yeah, some question you guys are posing, I know we have answered for it. They're coming next, so I will not interrupt Bob for those, okay?
So
But
one of the other issues is it is a requirement basically worldwide that an enclosure that's containing intrinsically safe circuits be labeled as such. So this is one of the things that I see quite a bit, that we'll see a panel or an enclosure or something that's basically without that marking. We want to see a marking that says that this enclosure contains intrinsically safe circuits. So what you see on the left-hand side, we see a junction box with some blue terminals in there. Those blue terminals are typically used for intrinsically safe circuits from a visual standpoint, but we notice that the enclosure itself does not have a label. The enclosure on the right does. So that's what we want to see when we're looking at enclosures that contain intrinsically safe circuits. The verbiage as to exactly what it should say does differ from country to country, but generally speaking, a blue tag, a blue label that says this enclosure or this box contains intrinsically safe circuits is generally acceptable most places of the world. So be aware of that. That's something that we do find quite a bit.
Well, I believe now, Bob, we have a poll. So let me
have a
launch.
poll
That's
question.
an easy poll, but it's a tricky answer. One of those answers that, you know, read it before you answer. True or false? All intrinsically safe cable must be light blue. I believe I have the answer, but I will not give it away. It's hopefully I made the poll single choice, not multiple choice, so you cannot make mistake. Okay, we got it's coming in. I think most of you guys are not getting it right. It's a misleading question. Not a misleading question, but the issue about blue cable can be misleading. Okay, I think we had enough vote. Let's share the result. Most of you have answered true. So Bob, is it true or not true?
It's not true. However, okay, there are many clients out there that say that their intrinsically safe wiring must be light blue. What the standard actually says is that it can be light blue, but generally speaking, what all of the international standards and actually the US requirements and everything else are all pretty much, if we're going to use a color coding to identify our cables, then light blue should be used for IS circuits. So that's where we do say light blue is absolutely a good means to identify our intrinsically safe circuits. However, I do know that there are people out there that run all over the place saying, I need to find light blue cable for my intrinsically safe circuits. If you actually read the standards very closely, the standard doesn't say that it must be light blue unless you're using a color to identify your IS circuits.
Esattamente.
So what you can do, okay, and this is commonly done, you can put cable tags, you can put markers, you can put some sort of identification on other colored cables saying that this is actually intrinsically safe wiring, okay? What we don't want to have is a cable on the right-hand side that is intrinsically safe or carrying intrinsically safe circuits, but not labeled, okay? So we do need to label it, but it is a big misconception out there that the cables must be light blue. That's not.
As a matter of fact, you know, most manufacturers like ourselves, for the terminal block, we use a blue color terminal block because it's easy to identify, more easy than having to put a label on it.
Absolutely. The point is,
I have a couple of questions, Bob, but go ahead.
No, the point is, this is one of those things where, again, we supply products as well, and people are looking and saying, hey, we have to have light blue cable. And I'm usually asking the question, okay, is this for intrinsic safety? Yes. Well, why are you needing light blue? Because it's mandated. Well, is it mandated from a customer? No, we're following this relevant standard. Are you using color blue for your indication of all IS? Yes. Well, okay. But in a pinch, you can actually, the standards do allow you to use other methods to indicate your wiring, and you do not necessarily have to use light blue cabling. It's good practice. I don't want to discourage anybody from doing that. However, all the standards basically allow you the option to do something else.
Yeah,
so,
and in fact, you know, we have a couple of questions. Both are similar. They are saying, what are the references? Where do we find this information in the standard for the labeling, for the blue color?
Right. So where you'll find actually most of this is actually those standards that we were referencing earlier on. So the -14 standard in the IEC world will give you that information. That's also located in the -25 standard. And you'll see that same information in both the NEC and the CEC, the Canadian Electric Code. So you'll find this information in there. And go ahead.
Sorry, Bob, I was saying I might take the effort after, you know, we will send you the information after the webinar, and I might take in the email, I might put some answer that we cannot, like what exactly is the reference page in the standard that you can look at.
Right.
Another question said, going back to the 50 millimeter, it says, can we reduce the minimum distance of 50 millimeter by installing a separation plate? I believe we show you that. We show you the answer, we show you the plate. If the plate is not plastic, must be grounded.
That's correct.
And we had another question. It says, I don't know if you want to answer this now. Let me see. How can we manage a connection between a machine and a cabinet containing 10 IS barrier? How can we manage an IS connection in order to be able to consider full installation of a single IS system? Might be a little, can you read that?
Yeah, I can read it. I'm not really sure what the question is, but let's come back to that one.
Okay. Let's move forward.
Number 5, incorrect gland selection or incorrect installation. So this is not necessarily just an IS issue, but one of the biggest issues that we see as an inspector of EX installations, regardless if it's EXD, EXE, EXI, whatever it is not installing the gland correctly. So that is one of the biggest issues. What we want to make sure is that when the glands are being installed, they're installed as per the manufacturer's recommendations. They are installed in accordance to the wiring regulations of whatever country you're following. And generally our default for many cases around the world is using the gland selection charts in 60079-14. And that information is located in section 9, if I believe. So that tells us what types of glands to use, depending on the protection concept. So that's really the important thing that we want to highlight and emphasize on glands. A couple things on cable glands. Number one, down at the bottom, we do not want to use Teflon tape. We see that an awful lot. On the right-hand side, you'll see a transmitter with what is called a traveling plug. That's a non-certified plug. We would want to make sure that that plug is replaced with a certified plug. We certainly can use blue cable glands, but it is, again, like the marking and the identification of cables, blue cable glands are not necessarily a requirement unless the client is specifically saying so. So we can use non-blue cable glands for running IS circuits, at least from the standard is concerned. So again, people can use them. There's no problem with doing that. Just make sure that they're certified for the application. And then finally, this is probably one of the biggest ones when we do an inspection on IS is we do not find a descriptive system document. I have done a significant portion of inspections on IS where I've asked the customer to provide me this information, and I get a look that is like, why? It's like I'm a unicorn or something like that. So the reason why this is important is that we need to, as an inspector, when we follow the inspection charts that are published in the 60079-17, that's one of the requirements. Because I mentioned to you very early on, this is a system concept. We have to take into account the associated apparatus, the cabling, the field device, and we want to make sure that everything that is actually there matches our DSD. So here's an example, and this came straight out of 60079-25 as an example. I won't go through all of this, but I will show you this is basically the information that what we want to see on it. We want to see our loop calculations, whatever components for use on that circuit, our wiring installation, the cable lengths and or types, any unique identification numbers, date and name of the signature of the designer, and if we're using any surge protective devices, we should have that as well. And again, we need to have a DSD to compare that to actually what gets installed in the field. This is, again, one of the biggest issues that as an inspector, I don't find this. And it's really the responsibility of the designer or the OEM to be putting this information together. And let me show you what we actually do when we put a DSD together. So here's an example that we get the parameters directly from, in this case, a beacon unit. So this gives us all the electrical parameters that we need to provide or do our calculations. Then we take the information, in this case, the resistance of this cable, which this information we could go through at detail, but I won't do it since we only have a short amount of time. But basically, we need to find the resistance for the cable. Then we take the output information depending on the ignition curve for the output barrier, which is all published. We take that information, and this is a little spreadsheet that we developed that we can basically plug that information in the yellow cells. We have to make sure that we plug in the information for the cable as well. And what this spreadsheet will do is basically say, hey, we're okay because our parameters match. But here's the important thing to note. This tells us, based upon this beacon in conjunction with this barrier, our maximum length of cable is 179 meters based upon a gas group of 2C. Now, that's why we want to see in our DSD, it should have the information as far as how long could this cable be without violating the parameters that we've set forth. So if we don't know that information, then again, as an inspector, how do we know? So what we can do in a situation like this, and I had this question here not too terribly long ago, a client had a particular GMI barrier in conjunction with a transmitter. And it was basically 30 different units, but they were all the exact same units. Same barrier, same transmitter. Did they have to actually generate 30 different drawings? And I said, well, depending on how you want to do it, you could have one drawing with 30 different tags if you want to do that. My suggestion would be just replicate the drawing and give it drawing number 1, 2, 3, 4, 5, 6, 7, 8, whatever it is. But this is really important to make sure that we have this. And we have it from an inspection standpoint because we want to be able to go back and check to make sure that that barrier that was originally installed is the same brand, the same product, and that the field device is the same brand, the same product. And very importantly, we want to make sure that that cable run does not exceed the maximum length. So when we take all that, then we know that this is a safe installation. So this is what is called our DSD, and this is the reason why it's important. So,
All right.
with that, I think we can go into, Paulo, do you want to bring up some of the other questions that we had?
Yeah, we have a lot of questions. One, let me take the last one because I will try myself out. He says, can you make a short summary of the mistakes at the end of the presentation? Well, I believe, if I remember correctly, we talked about grounding. We talked about segregation. We talked about marking. We have to have proper marking. Then we talked about
enclosure, cabling. I'm holding my, yeah.
And we talk about document, the documentation you need. There's one missing that I cannot recall.
Glanding.
Gland. In fact, somebody asked about gland. They said required to use. It says, do the gland have to be certified? If I remember correctly.
So this is somewhat of a sticking point. For circuits that contain a single IS circuit, meaning if we have a junction box that we have a single circuit coming in, a single circuit going out, the standard does allow you to use, and I want to double check this, but basically the requirement of the gland, it has to meet the impact requirements of 60079-0 and all that good stuff, but I don't believe it has to be a certified gland. I may be wrong on that, but that's with a single gland with a single circuit. And that's per the IEC standard. Generally speaking, I would say 99 times it should be a certified gland. The type of gland you would use would typically match up to the enclosure in which you're installing this equipment into. So a lot of times people will use an EXE, increased safety enclosure. We would want to use an increased safety gland. If it's an IS circuit that's coming out of a flame-proof enclosure, then we would need to use a flame-proof gland, okay? So we need to make sure that the gland matches the enclosure, that's first and foremost, and is suitable for the cable that you're actually running. So.
All right. Sounds good. Then we have a lot of people asking where are we going to get this information, the presentation. I joined late. As I mentioned at the beginning, all material of the presentation, maybe some additional material that we bring up from your question will be sent to you after the presentation, after the webinar, maybe a couple of days. We have to give our marketing guys the time to put it together. Let me see, before we go in some prepared question, which we got from your registration, let me see if there is any quick one here. Somebody asking about the DSD. Where can we find the spreadsheet calculator to download the DSD? I don't know if there is any spreadsheet. Is there, Bob?
There is. I have one. Just contact me or contact Paulo, and we can get you a copy of that Excel
Okay,
spreadsheet.
Great, done. Then somebody's asking if an IS and an EX device are the same. Well, you can answer that, but
not necessarily. No, an EX device could be various protection concepts. It could be EXD, EXP, EXE. So IS is EXI. So it's
somebody asking if the junction boxes that are IS certified are different from other types.
I'm sorry, are IS junction boxes? Yeah, that's kind of an interesting point. Most manufacturers, when they provide you an intrinsically safe junction box, they'll provide you a standard EXE box, and then they'll put an IS label or a label on there that says contains IS circuits, and they'll put blue terminal blocks in it. I think I've seen one manufacturer that actually did have a junction box that was certified EXI, and I'm not really sure how or why that was done. but generally speaking, most of the junction boxes that I'll see that are certified, they'll actually be an EXE junction box, putting blue EX terminal blocks and then putting a label on it, and that's certainly sufficient.
Great. In fact, you know, some product like our product, we have a EXIA certified multiplexer, which goes into the field, and all it requires an IP54 or NEMA 4X enclosure. It doesn't actually require an IS certified enclosure. Then, of course, it will contain IS circuitry. Right. All right, other question. There's so many, guys. I need to take my time. We some people are asking about how to calculate IS loop. We have some slides coming up. We have our own calculation tools online which you can go to. Let me see.
What I think what we can do, Paolo, is maybe we'll take a lot of these questions and we'll try to put that together to be able to maybe put something to send out to everybody.
Let me see, you guys are still with us. If you're still with us, let me share this presentation that I prepared, then we go through some more questions. Give me 1 second here, because I got too many windows open. Share, there we go. Does it come up? What do you guys see? Hopefully the right slide. You see my GMI webinar slide? Question and answer? Do you see? Do you see the question, how to use safety relay? Bob, am I sharing the right document?
Yes, yes you are.
All right, because you know, I don't see what I'm sharing, so I'm asking you, Bob. Okay. So this was a question we got during the registration phase. So Bob, the question, how to use safety when it comes to ICTS 6007946 equipment assembly. Yes, an answer, but I'll let you, Bob, run through it.
Right. So the IEC 60079 or the TS, and an IEC TS is different from an IEC standard. A TS is a technical specification, and it is in many cases it's a precursor to an actual IEC standard. And this was actually published here not too terribly long ago on talking about equipment assemblies. And where TS, this 46 really comes from is, say, for example, if we have an EX motor and we have some sort of overload that's protecting this EX motor, we're looking at it from an assembly standpoint. And also we have to take into account the installations. So say, for example, all of the installation requirements that are referenced in -14. So say selection of cable type, all the interconnects. So where this does come into play, a safety relay, you could say, yes, we as a safety relay, and if that safety relay, and we want to get this entire skid package certified under the -46 standard, then we would have to provide all those calculations, the safety parameters, all of that good stuff. So that's spelled out in 6.5 in the -46 technical specification.
All right, let's see another one. We have, if a component of a system is IS, then the system be considered IS. Or how to do that. Or also some of you ask about how to calculate IS circuit. And I have a few of the same question here came live today. So we prepare a few slides on that. Let's see if they make sense. I believe some of it you already introduced. You know, IS is an entity concept. It's not, you know, a magic box. It's something you have to put together.
Yes.
Right. I can go on. Basically, you know, I have, you know, you have your associated apparatus. You correct me if I'm wrong, Bob. Associated apparatus, which are the barriers, and then you have your field devices, and the two have to be matched to some extent. You have simple devices like a switch, a dry contact, or a resistor, which are considered simple devices because they don't store or generate a lot of energy. In fact, the standard defines these numbers here. I don't know if you guys can see it, 1.5 volt, 100 milliamp, or 20 microjoule. But you know, 20 microjoule, I always remember, is very, 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 very little energy. So those simple devices don't require certification, but all other devices will require some kind of certification. And then you need to match the two certificates. So the associated apparatus, so the barriers, and the field device. And we have an example here. I don't know if you guys see my mouse moving. It's EX certification, verification. So you have the maximum allowed voltage that the barrier will provide into the field. In this case, we have pick up as an example 30 volt, must be equal or lower than that is allowed by the transmitter in the field. So if the transmitter is certified for maximum 30 volt, well, the barrier should guarantee that no more than 30 volt are sent to the transmitter. Of course, these values sometimes are misleading because you think 30 volt, wow, I get a lot of energy out there, but these are not the no, these are under full condition, and we also take into account. I think there's a question a bit after. We take into account some safety factors. So actually, 30 volt might be 15 volt out to the transmitter.
Right.
And so you have to take. Some people are. We had a question about cabling. Cabling also need to be taken into account, right, Bob?
That's correct. We need to understand the resistance and the capacitance, energy stored within the cable. So we have obviously we take into account, in effect, a stored energy in a non-simple device, right? But we also have stored energy within cable. So we have to take that into consideration. And again, that's one of the big issues that people forget, is that we don't take that into account. And so we need to make sure that we understand that.
Yeah, but to make that easy, I mentioned earlier, we have online a loop verification tool. So something where you plug in this number and it will tell you okay or not okay. So you can download it. We can share this information. We had I don't know how far into we are about an hour in. Are you guys still with us? I hope we can continue. Let me see. It looks like most of you are still together. We have about the same amount of people that we started, so you're interested, so we can continue. We had the pros and cons. This was a question that came. I don't know if somebody asked. I will let Bob answer this, and I will look into the questions.
Yeah, well, go ahead, and I think this is just a summary, right?
Okay.
Typically, historically, Zener barriers were less expensive, right, than galvanically isolated products. Simple design, loop powered. You know, the one big issue with Zener is, as we mentioned, the requiring of the dedicated earth. The galvanic are typically more expensive. And in many cases, because they do contain a transformer, they have typically been larger and taller. So density, if you will, when you have a panel with a lot of barriers, that's usually been a big problem with galvanically isolated products. Now, GMI's range, they've come out with their new range that is actually a much thinner product. So we've taken the disadvantage of a galvanic and made it much more in line with a Zener type product. You do have to power a galvanically isolated product, but again, we don't have that dedicated earth. Sometimes the maintenance of Zener barriers is we find that we'll blow out the fuses or we do something to it. It's very easy to do that. And so Zener barriers, we have to treat them a little bit more with kid gloves during that initial startup. That's not to say that we can't damage a galvanically isolated barrier, but typically our Zener barriers are barriers, or during that initial startup, we have to be very, very careful because we will blow a fuse. Generally speaking, once a fuse is blown in a barrier, we typically have to replace them. Now, there are certain products on the market that there are Zener barriers out there that do have replaceable fuses. So we have to make sure, if we're going that route, to make sure that you replace it with the exact same fuse. Don't try to put a different fuse into a Zener barrier. Use the one that the manufacturer tells you to use. But again, most people don't have access.
Theoretically, Bob, the fuse in the Zener barrier cannot be replaced. You might have an additional fuse for safety, but there is an internal fuse which is part of under resin, so that you cannot replace it, because if you put the front fuse there, then the Zener barrier, it's all gone. I mean,
yeah, I've seen one manufacturer that actually touts the fact that they have a replaceable fuse, but I have
and they do. We also did in the past that Zener barrier, and we had the same solution. what happens is you put a second fuse with a lesser value on the outside of the Zener barrier or on a non-potted area, so you can remove it. But still, bystander, you have one inside that cannot be replaced, which is, so you have 50 milliamp inside, you put a 48 milliamp outside. So if you're lucky, you blow the one outside first.
Right.
We have, let me see, we have many questions about cabling, I want to go back here 1 second to this question which somebody asked about what is if we cannot manage to fit in this table? Well, there's not much you can do. If the parameters do not match, well then, unless it's a cable that introduces an error, meaning that the longer the cable, the more capacitance and inductance you have, you might have to shorten your cable. But if the two devices, the barrier and the field transmitter, by any or the field device of any sort do not match, well, they do not match. You need to look for a different device or a different barrier. Okay, let me go forward.
Paulo, there was an interesting question. I just saw it up.
Rose, go ahead. You can read the question, Bob, as well and answer them because there are too many for me to follow up.
So if a DSD calculation fails, what action needs to be done to pass the calculation? So, well, obviously, if we, that's an interesting one. If the calculation fails based upon too much capacitance or inductance in the cable, then the obvious solution is to do one of two things. Let's see if we can find a cable that has different parameters. That's number one. But we might be forced into a situation where we might need to place that barrier closer to the field device to shorten the length of the cable. Now, one thing that people sometimes fail to remember is a lot of barriers, including GMI, can actually be installed into a Zone 2, Div 2 application. So they're actually certified to be installed in a hazardous location. They cannot be installed in a Div 1, Zone 0, or Zone 1 application unless you put them, say, in a flame-proof or explosion-proof box. So that's one way you can address, possibly by shortening the cable.
Let me show you that. That is a question we had prepared an answer for, and that is exactly what it is. So you can install a barrier into an hazardous location, providing you have a separate type of method of protection, like here we show an explosion-proof box or an EXP box.
Right.
But also another way, we had a question on cable. I'm jumping here through the presentation, so sorry about that. But we had a question on cable, and one way I have a slide for it. I need to look for it. But the question was about L over R is another solution. It's another way. If the capacitance is too high, well, then you can look at the other parameter, which is if the inductance is too high. You can look at the parameter L over R, so the inductance over resistance. So there is several parameters you can look at.
Correct.
Okay, let me go to a question here. Why a cell phone cannot be used in Zone 0 environment? And that came from in the sign up. I don't remember who posted this question. We have an answer here. Bob, you want to take over this?
Oh boy. Yeah, well, so the protection concepts that are recognized for Zone 0 are either IA, intrinsic safety with 2 fault tolerance, or MA, encapsulation, again with fault tolerance. So a cell phone, there are cell phones that are certified IB, and I've seen them actually and they have 2 fault, or they have single fault tolerance. So I would say this, I don't know why exactly you could not use a cell phone other than they are not certified for it. And I assume it's because of the fault tolerance that you can actually achieve in building a cell phone, making it suitable for hazardous locations. So I have not seen a cell phone that's actually certified for Zone 0. I have seen
because it cannot be made, it cannot be achieved, that type of
I'm assuming, I'm sure the phone manufacturers would love to have a cell phone that's suitable for inside of tanks, but I have yet to see one, and I'm assuming it has to do with the fault tolerance of a cell phone. Could be
We try to
because of the path.
certify a zone zero device, and believe me, it's very, 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 very tough. And the energy has to be so small that the phone will not be able to operate. There's not enough power, you know, with the antenna power you can pour out, we only go, 50 meters or so. Because you have the energy limitation is very, very, very tight in zone zero, where you have a constant presence of danger. Okay, let's move forward. Let's see what we have here. Potential free contact with 24 volt DC relay is enough to trigger a fire? Well, I guess so. Here's an answer. I can answer that. Basically, even a simple device, we had that discussed this earlier. A simple device is a device that cannot store or generate energy by itself. So a dry switch is one of those. You can put it in anywhere you like in zone zero, but now you have two wires that come to the safe area. Now on those two wires, how do you control the energy? How do you make sure that nobody puts enough voltage there or enough at 24 volt? It can be 24 volt, 2 amps, and that would be above the minimum required energy to ignite in certain gases. So the barrier, that is what the barrier job is for, to make sure that the amount of current voltage, so the power on the other side of the barrier is limited to, this is a DI barrier type. So you have 10.5 volt, 22 milliamp, 56 milliwatt. It is certified for zone zero. So you can connect any switch that is in zone zero. So in itself, it's basically a certified power supply. Okay, I hope I answered the question. Anything to add, Bob?
No. That's a no.
I have somebody commented on our discussion on cell phone. He says it's not healthy to work in zone zero. Cell phone should not work in zone zero. I agree with you. And besides zone zero, where is zone zero? It's inside a tank. I mean, it's next to a relief valve of a tank. I mean, it's a very small area in the plant where you probably should not go anyhow.
Well, but there are some requirements, and there actually are pneumatic air powered, and old technology, there was actually what was called EXS, and there was light fittings for guys that needed to go inside of tanks and do inspections of tanks during the cleaning process. So there is actually some products out there that were designed specifically for use inside of tanks. But again, you're right. You would not typically take energized electrical equipment inside of a tank, and you would not want to do that. Okay,
so we have a question which I think is also responding to some of the other questions we have here. In which application can intrinsic safety be used? I think was one of the poll questions, basically, no? It's all low power applications. So we have 420 milliamp switches, voltage free contact, temperature, solenoid, those small solenoid valves, because the maximum energy you can send is 40, 50 milliamp. Strain gauges, sounder beacons, vibration, fire and gas. But it's used in a lot of industry. In our application, we've done mining, fueling of airplanes, distilleries, and of course, oil and gas. Also you, Bob, I'm sure you find many, many applications. Now there's a question, a very, very interesting question. Somebody posted a very, 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 very interesting question, which I had to look it up. Honestly, the answer is correct, I believe, but we had to look it up. So the question is, do inductance and capacitance of the cable depend on the isolation material of the same, whether it's PVC or polypropylene and so on? Beginning the answer might seem obvious, no, but in reality, here's the correct answer. You want to give this away, or should I read it through?
No, go ahead.
So the cable inductance, the cable capacity and resistance are stated by the manufacturer of the cable. They're given by meter, by kilometers, because they are spread along the cable. Now, inductance and resistance are not influenced by the cable insulation material, while capacitance is. And why is that? Because a capacitor is an expression of the energy stored between two cores. So the isolation between the two cores, or the dielectric constant of that material, makes a difference on the capacity of the cable. The better the dielectric constant is, the less capacitance you have, and the less capacitance, the better the cable, because you can go longer in distances. If I remember correct, PVC was not a very good isolation. They were better cable. Of course, also shield. Well, a shield is used, as earlier Bob discussed, to provide separation for IS security. It also introduced more capacitance, because now you have another core, which is the shield. So a shielded cable will have more capacitance. Okay, let's go forward. What is safety factor? This is a very technical question. I might want to skip it. I'll give you a few seconds because we are getting busy and we have a lot of questions still to answer. But basically, the manufacturer has to consider a safety factor when design his product. So those are the curves for different gas group. They're not the actual curve, they're a replication of the same. So there's a maximum voltage and a maximum current that you can use in gas second B, second C, second A, and so forth. And given a constant voltage, you need to be below the curve for the current. But the current is not the current stated, but the current stated under full condition by 1.5. But as I mentioned here, the short circuit current is taken into account by the manufacturer. So if we tell you it's certified for group second C, well, then it's certified for group second C.
Let me add something, Paolo. One of our guests mentioned about working in a zone zero environment. And if we said that you would be working in a zone zero environment while the tank is full, absolutely not. It should be vented. It should be cleaned before anybody does any work inside of a zone zero tank. So I apologize if I made it sound as if you should be going into a tank that's actually got the flammable materials in it, because that was not my intent. So I just wanted to clarify that. If somebody
misunderstood people that lost their life in such cases, so yeah, gotta be very careful with maintenance. Also in maintenance, in Italy, not long ago, we had an accident. Several people lost life. Okay. Well, we had a lot of you asking if we have arranged other questions about intrinsic safety. Sorry, yeah, also intrinsic safety, but safety relays, functional safety. We do. We have many webinars. They're online. We have. We can share you the link. You can go live on our webinars, and we have many. We have functional safety, safety relay application, and so on. So let me stop sharing this. I believe that was the last answer I prepared. Yes. So let me stop sharing this and see, Bob, if you guys are still with us. We still have about 14 unanswered questions. I don't know if you can get to it. Say, for example, okay, the vented question you answered correctly, so let's say done.
There's one question. If you cannot find the minimum ignition energy to ignite a particular flammable gas, how do begin to protect an electronic sensor that is to operate within the explosive atmosphere or this flammable gas? Well, yeah, that is a great question. I'm not really sure how to answer it. And again, the point is, if you use an IS barrier to limit the energy, you still may not be reducing it low enough since you don't know how low it has to be. Absolutely correct. However, there is a 60079-20-1 standard that gives properties of all the gases and vapors, including the MIE, the LEL, the UEL, the density. So most industrial gases will be listed in that. So if there's a particular gas that you cannot find within that document, I would suggest we also look at maybe an NFPA document. There are some other documents out there that do reference other gases that aren't necessarily listed within the IEC standards. So, but yeah, if you don't know that information, if you don't know what gas group it is, then trying to select a barrier for that is you have to know that information. So, yes.
Okay, let's see. Well, we have a question about search devices. Search devices, SPDs, are not, they are there to protect from lightning strike, from, you know, accidental high voltages. They are not there to protect IS security. They can protect IS security. They are also, I believe that we do have IS certified surge protection. So when you put them in the field or in front of a barrier, they require themselves to be intrinsically safe certified, but they're not, they cannot substitute a barrier.
That's correct.
All right, see more questions. If calculation failed, what resolution to be considered? Well, I think we discussed that. You need to find an alternative way, shorten the cable, find a different manufacturer, replace the device in a different area.
There's a question if a transmitter is installed with a certified gland, EX gland, using an armored cable. You have to run an earth wire from the gland brass banjo to the earth stud on the transmitter if fitted. If it's an armored cable and we're using an EX gland that is certified or is a gland, for example, like a 501-453 universal or something like that, where the armor is actually tied into that, and the transmitter is a cast transmitter, meaning that it's a cast aluminum or something like that. Generally speaking, that would be sufficient, and the requirement of actually having an external earth wire to an earth stud would not necessarily be mandated. That being said, there may be a client, there may be a requirement specifically for somebody. Yeah.
Sorry, I will post the question so people can read the question while you answer it, because it might be a little,
right,
you know, hard to understand.
And it's assuming that the transmitter is bolted using a metal flange to a metal tank that is earth. So generally where we say that earth tags are required is typically if we're using a plastic enclosure, where we're going through a clearance hole of some sort, and we don't have an internal continuity plate on the inside of our plastic enclosure, then we definitely want to be using an earth tag to be able to tie an armored cable to the earth tag, which in turn is attached to the structure or to an earth stud on the enclosure itself. Generally speaking, if we're talking metallic enclosures, we don't have to go through that route. That being said, again, that's generally to IEC standards. In Canada, the US, don't take that as gospel, because we have to follow either the CEC or the NEC. And again, some clients will say, no, I want to see that earth stud. I want to see that banjo. I want to see that external earth. And so just because the standard says you can do something doesn't necessarily mean that that's in compliance to what you or your client would expect.
All right, Bob. So we have a question that should be easy to answer. For simple device like non-EX junction box, but that include IS security, the non-IX cable gland are okay or not okay?
If it's a junction, what was that? I'm sorry.
It's a junction box,
right?
Non-EX, but include IS security. So first of all, can we have a junction box that is non-EX certified with IS security inside?
Of course. Of course.
So in this case, do we need to have the cable gland certified?
Well, it really depends on where this junction box is located, right? If it's located in a safe area, right, it's a cabinet, and it could be in a control building or analyzer shelter or something like that, then that's considered to be a non-hazardous area. So the wiring methods generally at that particular point, and this is a generality because it's different in different countries, but generally speaking, a non-EX certified gland would be perfectly acceptable at that point. On the other hand, if we have a junction box that is located in a hazardous location, then, and again, forget division applications, just thinking about zone applications, generally that junction box should be certified for that particular application. The glands, even though we have non-IS and IS, they should both be certified for that application. Yeah. Generalities.
Yeah. Very good. Okay. Now, do you, well, I think we answered this question before. If you install So do you install surge protector after IS barrier in zone 0? You can install a surge protector in zone 0. I'm not sure. In zone 1 maybe certified for, but zone 0 not. But you can install a surge protector in the field if it is properly certified for it.
Yes, but I think, if I'm not mistaken, Paulo, the surge protector would be mounted before the IS. It would be upstream of the IS barrier.
Yeah, it will be. You can have two surge protectors, one sitting right in front of the barrier on the control side cabinet, and one in the field, say, to protect your transmitter. That has to be certified for, typically are EXD certified, to be installed on an EXD transmitter. Let me see, how do they detect short open circuit fault up from relay? Because this is a tough question, guys. It's also, maybe I should read it before I read it between myself before I can read it out loud. So it says how to detect short open circuit fault output device from GM relay because PLC connected up to relay. But field side open short circuit PLC, no sense. Okay, well, this is more of an application question that we will answer in our smart safety relay webinar. But basically, what you have to do, you have to use a safety relay which has a built-in line monitoring capability and transparently transfer this information to your PLC, because obviously the ability to read, when you put a barriers of any kind of a relay between your field side and control side, you are putting a wall, an isolator. So physically some information cannot be transferred. They have to be designed to transfer such information. And there are products available, we will get to it, but different webinars. Let's see.
A simple device.
What about Profibus and Modbus and LAN cable? Are intrinsically safe or non-intrinsically safe cable? That's a question.
Well, there isn't really an intrinsically safe cable per se. We can use Profibus and Modbus and LAN cables for intrinsically safe circuits. So,
all right. In fact, we have, there is FISCO standard, no? That defines.
That's right. It's the -26, I believe it is. I may be wrong on that, but there is a FISCO standard. So, but generally speaking, people ask sometimes, are there certified intrinsically safe cables? There isn't really a certification that goes along with cables to make them intrinsically safe. It's how you apply them.
We had a question about how do you classify simple device. I believe we answered that. In the standard defines a certain amount of energy.
Device, right. About one. Yeah.
Yeah, so
we answered that one before, but basically about
sometimes can be misleading. Bob? For example, I often come across this application. An LED is an LED a simple device. It's just a semiconductor inside, but in itself, it's not a simple device.
If you think about it, if it's an energy storing device, right? Anything that's potentially energy storing is generally not a simple device. If it's a non-energy storing device, generally, again, these are generalities, but the details, I think we put those in the presentation, but they're also listed in the standards.
There's also another point to be taken into account, which is temperature. When you classify a device for field installation, it has to be classified temperature. So a temperature class, T4, T5, T6, because a gas can also be ignited by mere temperature. Some gases, I don't remember, but I think like 80 degrees, they will go on, they will be ignited or even less. So an LED in that case, it can be a hot spot. It's small, maybe very little energy, but it gets very warm. That has to be taken into account, right? It
does, yeah. Most of your gases have ignition temperatures of above 200 degrees C. There is a handful of gases that have very, very low ignition temperatures, but we definitely have to take that into account when we're putting heat-producing devices into those areas.
All right, guys, we're coming up. Well, it's been 90 minutes. We are, but a couple of last questions. I don't know, probably if you want to answer. For example, why do we have to take into account the resistance value of the cable?
Well, resistance creates heat. I mean, that's part of it.
I think the question may be more like in the cable resistance, of course, the more resistance, the more voltage drop you have. So the worse the cable is, the less energy is transferred. But at the same time, from a safety point of view, the resistance counterbalance, we said is only the inductance. So you take into account the resistance of the cable when you make the calculation for inductance, L over R. All right, I think we have done most of it. Is an RTD a simple device? Yes, it is a simple device. Anything else? I think we're, well, we've been together for 90 minutes. It's time you to go to your wife and I go home for dinner, because for us, it's kind of late.
Oh, so it's only 10:30 here, so it's all good.
It's only for you, but for me, it's not. And guys, we thank you very much, all of you, for being with us. We enjoy very much your questions. Hopefully you enjoyed our answer. We will share all the information, as I said, via mail soon. In the presentation, you have Bob and my contact. You can contact us. And look into our website for the following coming up webinars.
Yeah, and I just want to echo that too. Thank you so much for your time, attention. We appreciate that. Hopefully we provided some good information to you guys. Again, realizing that this is a worldwide presentation, I didn't necessarily give you some real good definitive answers to some of these questions because there are exceptions to so many. So I really, really do want to emphasize, wherever you are, look at the relevant standards and rules and regulations in your part of the world as far as making those determinations. But in generalities, hopefully you learned a little bit more about some of the major faults and problems that you will find with IS. And
we have a lot of thank yous. So thank you again, guys. We'll see you next time. Look out for our webinars online. Ciao. Ciao, Bob. Enjoy the rest of the day. Ciao, guys. Ciao, ciao.